Hello again, physics class. I'm so glad you joined me for the last part of this, which is elastic collisions. So remember, inelastic collisions, one object ends up inside of the other, so they stick together, right? Become one object. For elastic collisions, it's something very different. For elastic, E, energy is conserved. Okay? So for these elastic, remember, E, energy, elastic, energy is conserved, right? So these types of collisions, the energy is actually conserved. Usually, in almost all cases, we can't assume this, right? Because when objects collide, generally there's some sort of friction created that creates heat and we lose energy there. Or maybe the shape of the object changes, we lose energy there. But in elastic collisions, the energy is conserved, okay? Most collisions are neither of these, okay? So you can really think of it like kind of like opposite ends of the spectrum. We have elastic over here. We have inelastic over here, okay? But most collisions sort of occur somewhere in this area in between, right? So these are like the two special extreme cases. Remember, elastic means energy is conserved. Inelastic means we end up with one object at the end. Two objects stick together. Okay? So we can really write this out as two formulas, right? So we have the same exact formula that we had before, where we have something like mvi plus mvi equals mvf plus mvf. Okay? Now, one thing I did not say earlier is that specifically it's the kinetic energy. Okay, so specifically it's the kinetic energy that's conserved. Now, if I have two objects, each one of these has a kinetic energy. Okay, so it'll look something like this: 1/2 mvi squared plus 1/2 mvi squared equals 1/2 mvi squared plus 1/2 mvi squared. Okay? So this actually gives us a second equation. Okay? Sort of the normal example that people give for elastic collisions would be pool balls, right? You're playing pool, you do this thing, right? So that's that playing pool with the billiards ball or whatever you want to call it, is an example of a elastic collision. Okay, let's go ahead and look at this question. I'm actually going to go through and change these masses. These are sort of the realistic masses. I'm just going to kind of simplify it. So let's simplify this to 1. Let's simplify this to 2. Okay. So we're just kind of simplifying it a little bit so our numbers are easier to look at. So I have marble 1. So I have my two marbles, marble 1 and marble 2. Okay. So this is marble 1. The 1 kg marble moving to the right at 0.225 meters per second. So that's m is equal to 1 kg. Vi is equal to 0.225. Okay, makes a elastic head-on collision with so mass equals 2 kg. Initial velocity is 0.18. Let's go ahead and look at our axes. Let's make right positive, left negative. So the shooter marble, my second marble, is going to be moving to the left. So this is going to be a negative. Okay. After the collision, the smaller marble moves to the left at 0.35 meters per second. Okay. So this VF is now going to be negative 0.315. Okay. And then assume they're not rotating, we don't still have sort of other factors that are causing problems. What is the final velocity of this second marble? Okay, so we're actually not going to need to worry about this aspect. Okay, we could use this, or we could use the regular momentum one. Okay, so either one of these would actually solve the question for us. Let's go ahead and use this. Well, let's go ahead and use this. Okay. what do you notice about all these 1/2? Yeah, if I have the same factor in every single term, I can actually get rid of it. But let's go ahead and write it out for practice sake. Let's just start with our EI equals EF to show that we know energy is conserved, right? And then we have 1/2 mvi squared plus 1/2 mvi squared equals 1/2 mvf squared plus 1/2 mvf squared. Okay. Now I should be able to do this both ways and get the same answer for both. Okay. So let's go ahead and do it this way. So I have 1/2 times 1. Actually, remember, what cancels out? The 1/2. So let's get rid of that. Cross, 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 cross. So I have m, which is 1 times 0.225 squared plus 2 times vi, which is negative 0.18 squared, equals, and then I got 1 times negative 0.315 squared plus 2 times Vf squared. Now, the one problem with approaching it this way is I actually get rid of my direction. So this answer will tell me nothing about the direction it will be traveling, okay? So now we're just solving for Vf, okay? I think I will let you work out this part. You can also see the answer on the notes, the answer key to the notes, but I'm not going to work it out here. Let's go ahead and set it up the other way as well. So let's go ahead and set it up the normal momentum way instead of the energy way, so you can see that. So we're using this formula. So I have m, which is going to be 1 times 0.225 plus my second object, that second one, is going to be 2 times negative 0.18 equals, running out of room here, sorry. I'm going to put the second side of the equation down here. So then I'm going to have 1 times negative 0.315 plus 2 times Vf, okay? Both of these equations should give you the same answer, okay? So it just kind of, elastic gives you this ability to kind of give more information about what's happening, right? So now we know that the kinetic energy is conserved. Thank you for joining me for all of these practice sets. I hope you have a lovely break if you're doing this over Thanksgiving break or if you did it last weekend. Thanks so much for tuning in to all those notes. Remember, if you get stuck on a particular question or you really need help, send me an email. I'm happy to answer your emails, unless it's really late at night, because I go to bed early. But make sure you send me an email if you have a question, and hopefully you're able to solve these answers and be able to learn momentum. Okay? Thanks so much. Bye.